Good morning, students. Well, we've been to the through the winter blast, and now we're back to springtime. Uh, the, Last week was challenging, and I hope that everybody is back to some sense of normalcy. We often get very comfortable in our lives and don't think about things that we often take for granted. We don't take the weather for granted anymore. I'm sure we always talk about how it varies so much, but the the thing is, and this reminded me a lot of was Hurricane Harvey, and how we always endure. We always get through the tough times, and so hopefully you're in a situation where things are starting to improve and get better. There are certainly many services through San Jacinto College if it turns out that anybody needs any additional assistance. So please take advantage of that if there is certainly a need. I give to the San Jacinto College Foundation for that very fact, because it's important that you all get what you need. Um, as I emailed last week, I extended the due dates and was also able to get up our second lecture, which again was pretty much to go back through some ideas from work in the center of mass and then present the review of the integration. So that material was more review and maybe not so much new ideas. So hopefully that will be a good transition point for you for what we do today. So again, I'm glad to see you all back and grateful that we had the blessings that we did. Our friends to the north certainly uh, had a much worse situation, and so I guess there is a blessing to living in Houston. Warm most of the time, and so we got bad, severe cold weather, but we did not get the extent to which others did. So we are truly blessed, and I am grateful for that, and I know you are too. So today, ladies and gentlemen, what we want to do is to cover the topic called integration by parts. And this, I'm pretty sure, is something you did not do in your previous class. You did, however, study the product rule, and we've used the product rule many times. Well, maybe not so much in this class, but you certainly used it quite often in Calculus 1. So what we want to do is take the uh, derivative formula for that of a product. That is it's sometimes called Leibniz rule, and recast that in terms of an integration formula. So the concept was already there. It's just we didn't talk about it. So let's talk about it now. So I think you'll find this to be not only illuminating, but very interesting, and maybe like we had the du over u form to fill in for the power rule, this will be a nice technique that fills in for many integrands of products that we just can't do, and now the door will be open for that. So as I said before, this is called integration by parts. And what we want to do is consider differentiable functions. This is the notation that we usually see for integration by parts. Consider differentiable functions. Let me grab there we go, get that as clean as I can. Differentiable functions u and v. And what I do is I always write the V's like a Greek nu, so you can tell the difference between the U and the V. Not to be obtuse, but just to make sure that you can differentiate the two in the sense of telling them apart, not their derivatives, of course. So we have so the differential formula that we had in Cal 1 is just basically the product rule. So we'd say the differential of u times v, in this case, will be v du plus u dv. So again, just like you did in Calculus 1, the differential, basically you focus on one function and then flip it and focus on the other function and just take their products. So we've got the differential of a product and now we want to integrate. So now integrate. So we'll have the antiderivative of the differential equals the antiderivative of the sum. Now, of course, the antiderivative and the differential undo each other, inverse processes. And then now here we can use the linearity, and we'll just basically couch any constants of integration in the integrals that remain. So we're not being sloppy. We're just saying we're holding off on writing that to have a cleaner formula. So we embed basically the constants into the integrals that are left in the formula. So now we have the linearity. So we have v du integral plus the integral u dv. And now it's customary to solve for this integral. Again, this, you ask any calculus student, and even the ones that maybe decided math was not for them, they remember integration by parts. It's one of those things that sticks with you. So you have the integral of u dv, and so we just subtract this integral from the uv. So uv minus v du. So the differential form is very convenient. Physicists, I always say this, physicists and engineers love the differential form, and we can thank Leibniz for that. Newton had a very nice form that as a more of a scientist form. Newton was everything: scientist, chemist, mathematician, philosopher. I mean, he was a true Renaissance man, but Leibniz afforded us this notation, which we still use today. So the idea is that, like, oh, okay, so we really already knew this, right? And my answer to that is actually yes. So now what you can do, and if we can think of this symbolically, is that we see that the integral here has an integrand that basically has two parts. It has a u and a dv. And what we want to do is make an assignment for each of those. And then when we look on the right-hand side, from the dv, we need to extrapolate the v, and from the u, we need to extrapolate the du. So we have to do calculus to get v from dv, and we have to do calculus to get what? Du from u. So what we're thinking is that we can simplify the problem. That is, hopefully the calculations will be doable and move the problem forward to a closed form antiderivative. So symbolically, what I like to do, I like to organize this. The idea is that there's certain methods that we can adopt that will definitely be useful to us to streamline the process when the integrand is maybe of a certain form. And it doesn't lessen the power of the integration by parts. It just makes the process easier. And what we like in calculus is to streamline processes so they're more efficient, and plus they help us to keep up with all of the signs and all of the variables in a way that hopefully keeps us more correct. So often in calculus, we're always plagued by the fact that there's so many ideas to maintain. So I think you're going to find that the techniques we learn with this will be very useful. So for instance, what we can think of is choosing a u from the left-hand side and a dv. And for the first few examples, we'll always put in the complete notation, but there'll be times when we'll relax the notation and not lose any content, excuse me, just keep the notation simpler. And now, in order to move to the next side, what we're thinking of, we differentiate or take the differential to get du, and then we anti-differentiate the dv to get v. So these are operations that we need to be able to do. For instance, we look at the integrand and we say, well, can't do much with this. But if we break it into two pieces that have simpler calculus, then we can merge that calculus to get an answer. So the UV, we can simply write as an arrow here. And now you're thinking, I don't really need to attach a sign, but later on, we're going to find it very useful to attach a sign to this diagonal. So this will just be a plus, even though that's really not going to change anything. You're thinking, well, that's useless. Plus is not going to make the sign different. And I agree with you. But later on, this will be very useful. So we'll go ahead and put it in for now. And then what we'll see is we need to do an antiderivative. So we need to do the antiderivative of v du. So we're going to do a horizontal line and remind ourselves of the negative sign. So in the integration by parts method, we're going to think of connecting terms with diagonal lines to create products, just like we have here. And when we connect two terms with a horizontal line, it may carry a different sign. That is, this sign's going to alternate as we apply this a second time because of the minus here. But when we have a horizontal line, we will drag along the integral. So we see the integral of u dv is uv minus the integral v du. So this is kind of a symbolic way of notating this to keep up with everything. So we would say this would be the equivalent of this computation. So in order to do this, we do this computation, which is the right-hand side. Now, what I wanted to do is start out with some simple ideas to get you used to this, and then we can grow with this. You'll find this to be very useful, but I will say this, stick to the notation that I give you because it will help you to set up good strategies. Otherwise, if you're always starting, from ground zero, so to speak, problems get really long. They're already long enough, really. So we're going to try to make things as efficient as we can. So the first problem I want to do is the integral of the natural log of 5x dx. Now, when you look at this, you're thinking, well, we're fine with differentiating natural logs. We learned that in Cal 1, and we know the du over u form. But this is outside of that. Now we're thinking, okay, well, what's the antiderivative of the natural log? And that's really a question we've never had to answer. And so when we think about this and we think about this selection process, we think about assigning variables to these particular terms here in a way that we can move the problem forward. So we don't want to make assignments that make the problem harder. So first we say, okay, well, we can make the ln of 5xu because we can take the differential of that. We know how to do that from calculus 1. So first we'll just say u, do this very formally, is the natural log of 5x. And then that only leaves dx for dv. dv equal dx. Okay, so again, don't worry about the assignment and like, oh, well, what if I mess this up? No, it's like when you do integrals, you're thinking you start one way and it doesn't quite work, then you try another method. So don't be upset that you have to change this. That's part of doing calculus. So now the du, again, remember we reciprocate, but that constant just goes away by the chain rule. So du is just 1 over x dx. the constant just absorbs. So that's easy. I mean, you're thinking, wow, this is a lot simpler. Well, hold on, right? So now when you look at the dV, we just need to integrate. So in this case, when we think about this particular case, what are we going to do? Well, we're just going to say the integral of V will just be dV will just be V equals X. So this is kind of like what we did when we just first started learning about the notation of antiderivatives. And it's like, well, when I anti-differentiate one with respect to X, I get X because X prime is one. Okay, so just the basics here. Now you're thinking, okay, well, that wasn't so bad, kind of different, not used to it. But now we're thinking, okay, we need UV, so we can just go ahead and do our diagram here. Again, this is always the goal, and this helps us organize the work. Feel free to use this. Now, Dr. Larson usually does this type of setup, and in some cases puts in the arrows, not always, but his approach in the textbook is very similar to this. So now we go back to the integral, and we just see that we have x times the natural log of 5x. And then, of course, we have minus the integral v du. So we have x times 1 over x dx with the minus sign. So notice the minus sign here. And remember, the horizontal lines retain the integral. So let me do this in the order, not that it matters. Well, I actually in this case, let me just go ahead and write the v first, just to be, consistent, even though it really doesn't matter. So at this point, we just have x ln 5x. And then, of course, the x and the 1 over x absorb. So we're back to the beginning problem. Now, you're thinking about constants of integration. Don't worry about the constant of integration until the end. You can substitute it there. And of course, if it's a definite integral, then we'll slap the limits on this and the limits on this, just like we normally do. So this will be x ln 5x. And of course, we just get a minus x here. And then we say plus the arbitrary constant. So what you're seeing here is that the integration by parts will give you an antiderivative in closed form when this process works. And of course, you look at this and it's not an easy check. I mean, with the product rule, you're seeing that you're going to get antiderivatives that are rather unusual. And so now you look at this and say, oh, okay, we could have done, what's the could have? We could have done this in Cal 1. You had all the machinery to do this, but again, we just have to, end the topics in Cal 1. They're enough already. So the groundwork for this was already set in Calculus 1. So now, not only do we know how to differentiate and we know du over u integral form, now we can integrate a natural logarithm, which is fairly simple now. So what I'm saying is that the integration by parts is going to open the door to lots of antiderivatives that just seem to be off in left field. And now the door opens and it's like, wow, you're going to find that the integration by parts, almost like substitution, is probably one of the most powerful integrating techniques. And there are many, and their integral tables go on forever. They're voluminous. But you will find that parts will be a very, very effective tool. And this is one that students enjoy learning. So maybe you'll find this to be somewhat fun to do. I was going to say entertaining, but math is not entertaining. Math is hard work, but the rewards are worth it. It's when someone says, "Oh, make it fun, make it fun." Well, no, it's fun when you know how to do it, but the fun process is limited. Okay, now what I want to do is to, again, look at an example just to get you thinking about some trig functions, and then say, okay, well, it worked this way. What if we had done it this way? Kind of as a segue to the next section. So let's just look at this. I just made this one up. The square of cosine of 3x dx. Now, this is going to showcase a very important technique. Okay, I don't. One thing about integration by parts is that you've noticed it's algebraic. We have an integral equal to a formula, and we can move things around if necessary. And you're thinking, what happens when the integrand comes back again? You know, maybe multiplied by some constant. You've got that same integral, and it's like, how do we deal with that? Well, we deal with it algebraically. So I want to show you something here. Do this problem two ways. First, this is a product, so I'm going to write it, well, it's a square, so I'm going to write it as a product. So I just put a little dot there. And you're going to think, boy, this is a difficult way to do this. But I want to make a point here that shows a very important technique that's available to you with integration by parts. So say we did this, it's like we don't have much choice, do we? So we'll say u is cosine 3x, and dv will be cosine 3x dx. So being, again, very formal. And you're like, okay, du, again, the derivative of cosine is the negative sign. So we have negative sine 3x times the derivative of 3x, which is 3 dx. So I'll rewrite this. Sometimes you can just do this in one line thinking about the antiderivative, or the derivative, but it's good to go ahead and break it up. So we have du is negative 3 sine 3x dx. Okay, now we're thinking, all right, well, we need to do the antiderivative here, but the antiderivative in this particular case is the positive sign. So when we differentiate cosine, we get negative sign. When we anti-differentiate, we get the positive. But now we need to make it table ready. So we need to have a 3 there. So we're going to do a 1/3 cosine 3x times 3 dx. So this is table ready, right? Just like we do all the time. We don't even often think about it, and unless we forget it, then it becomes very important. So now when we anti-differentiate, we're going to get 1/3 times the sine of 3x. So the idea here is that this is what we normally do when we're doing antiderivatives. So this is, like we say, table ready. And so now we can say, all right, well, diagonal line, and then the minus with the integral. uv minus the integral v du. So our original integral is now, notice we have a 1/3 sine 3x cosine 3x. And now we have the minus. This is why this setup is good, because it helps you keep track of the minuses. We have minus minus, so we'll get a plus. So plus, so we'll have 3 sine 3x times 1/3 sine 3x dx. So now we're going to do a little bit of just you know, cosmetic stuff. This is just a trig identity here. That's 1/2 sine of 6x, sine of the double angle, right? That's a good identity. And of course, here the 3 and the 1/3 absorb, and we get sine squared 3x dx. Now, of course, this will give us a 1/6. And now here, we're thinking we need to get back to the original integrand, so we're going to rewrite this as 1 cosine squared 3x. So now we have what? Plus the integral 1 minus cosine squared 3x dx. So this gives us 1/6 sine 6x plus the integral of 1, or just dx, minus the integral, which is our original problem. So this is what I was talking about. We have cosine squared of 3x dx integral is equal to 1/6 sine 6x plus, well, that'll be x, and then another copy of it. So algebraically, we can simply add this to the left-hand side. So this becomes an algebraic equation in the integral. So equivalently, we have, sometimes we can even call it by another letter so we don't have to write the integral down again, but this is fine. So we have 2 copies of this when we add this to both sides. And so this will give us 1/6 sine 6x plus an x. And then, of course, now we can simply divide by 2, and we have the integral of cosine squared 3x dx. Again, divide by 2, that'll be 1/12 sine 6x, and then, of course, plus 1/2 x, and then we can tack on the c. So when you look at this, you're thinking, okay, that's integration by parts, but you're thinking, you know, you use these trig identities here, and wouldn't that be a way to do it too? Absolutely. But what I wanted to showcase here is sometimes we are stuck with this algebraic process. That is, we applied integration by parts once, and then when we apply it, we get an integral that's like, well, that's really how we started. We started with cosine squared. Now we have sine squared. It seems like we're just kind of going in circles. So then we say, okay, well, we understand something about sine squared. It's 1 minus cosine squared. And so that creates the algebraic equation in the integral. And so this is a common quality of the integration by parts process, that the actual integration becomes algebraic as equation solving, and that's what makes the technique so powerful. So now you're thinking, okay, well, say you're in the next section and you're thinking, well, Professor Ron said we need to do it this way. This is quicker. Or you're in a PDE class, partial differential equations class at A&M or U of H. You're getting your engineering degree, and you see all these trig integrals, and you're like, well, I'm not doing parts. That's crazy. That takes forever. You know, I don't have to do it. So here's an alternative, and this is something we'll use very often. But like I said, sometimes it's better to show you a certain quality of a technique with a problem that's easy to see. And this type of technique here, we will see again today. So what we can say is that, well, you know, back when you take your pre-cal, you're thinking, well, why not use the power reducing identity? Because if we can reduce the power from the square to the first degree, then the integral should be a lot easier. So here's what we're going to do. We'll use power reducing, which is kind of our mainstay when it comes to even integer powers of cosine and sine, power reducing. And you're thinking integration by parts is power reducing, as you can see. So this will be what? 1/2 1 plus cosine 6x. So the power reducing identity, remember, it's the double angle formula. So you have 1 plus the cosine of the double angle divided by 2. And again, that comes from the sum formula for the cosine function. So now you're like, oh, well, I can do this, Professor Ron. So we've got a 1/2 dx plus 1/2 cosine 6x. But now with this 6x here, just like we had up here, we need to make this table ready. So we'll say times 6 dx for the u, and then of course pay for it. So we need a 1/6. So now this is table ready. So this is, yeah, I'd say this is quite a bit quicker. Table ready. And so now we get the 1/2 x. And of course we have the 1/12. And the antiderivative of the cosine 6x is the sine 6x. And then tack on the constant. Well, that was very fast. And so we have the same result. Now, the thing is that even if you get an equivalent antiderivative, it may not always look the same. And why is that? Well, I mention this to you all the time, is that functions with the same derivative differ by a constant. So sometimes when things differ by constants, it's not obvious. I mean, it's like +1, okay, the difference is 1, but if it's more algebraic, especially with trig functions, you may not always see it. But I tried to write these in ways so they would look the same. So just remember that when you're working a problem, maybe you're working with a classmate, and you compare and say, well, I didn't get that. Well, don't worry about it. It may be that both answers are entirely correct. It's just that, again, trig functions and log functions get very mysterious looking. Even algebraic functions will give you answers that look wrong, but they're actually correct. And then, of course, you spend 10 minutes trying to show that they're equivalent, which gets crazy. So again, just remember, often a different technique will produce something that looks different. However, it is entirely equivalent. So what I wanted to show you here is that the integration by parts method is necessarily algebraic. And we need to be aware of this fact because there'll be times when we will rely on it. We will rely on it to get nice formulas for our integral table, okay? And so it's not a bad thing. It just means a little extra algebra. But when we compare the two, we're thinking, when we have cosine squared or sine squared, let me just remind you, we'll just go with the power reducing. So for instance, let me just remind you of these. So cosine squared u is just 1 plus cosine 2u over 2. Just like what I did right here, but I put the 1/2 to the side. And then of course, sine squared u is 1 minus cosine 2u over 2. So these are the power reducing, and they are very, very, very handy. And we'll use them over and over. Okay, that we're stuck with them, but we're glad to have them. But even powers of these functions, more algebra. I mean, the odd, we can move those into a substitution form and knock them out in no time. But with these, we are kind of stuck with the algebra unless you want to use a reduction formula that's based on integration by parts, but then that requires you remember that. But most students find this not too bad. They can remember it. So it is what it is, right? Now let's look at some other examples just to kind of make sure that we're happy with the technique. So you can see this is a interesting technique. So let's look at this one. Now, how you choose to work your algebra and how you want to move constants around is completely up to you. There is no set way to do anything. You can move constants in and out of the integral sign, and how you want to do it is up to you. But if you factor something and you're doing integration by parts, don't forget what you factored. After you do all those steps and you forget something you factored at the very beginning and wonder why the answer didn't come out well. Okay, so just be aware that this is a more tedious process, or at least more time consuming, and factoring things can, I used to say in grad school, when I was doing probability theory, I always told the professor, I said, just leave everything inside. That way we won't forget it. And he'd always laugh at me like, well, what do you mean? I said, well, I'm just thinking about what I'll forget, and I think he eventually understood what I was saying. But it's just a quirk that we have when we work things. So when we look at this, and again, what we can notice here is first, we're thinking, well, we'll just go ahead and write this as a product using the laws of exponents. So we'll say 5x times e to the negative 2x dx. So if we think of this using the laws of exponents, we can see an easy u and an easy dv, okay? And then what we want to do in our choice is that when we do the integration process, we actually, when we slide across the integral of v du, we want that integral to be easy, okay? If it's more complicated, then we might need to switch the choice of u and dv. The idea is we want the integrals to be simpler. If they get more complicated, then we're thinking, okay, can we make a substitution and do like we did on the last problem and make it algebraic? That door is always open if we can do it. So again, don't worry that your initial substitutions may not quite pan out. That's the process of learning. So here, what we can do, we'll just keep the 5 inside, even though, you're thinking factor it. I'll just leave it inside here. So we're going to let the u be 5x and the dv be e to the negative 2x dx. So when you think about these types of problems and you think about what we're doing, you're thinking, well, we can integrate this. This is not a problem. That's a standard problem that we do all the time. That's easier than the sines and cosines. And of course, this is easy to differentiate. So what you can do here, now again, a lot of times I just remind everybody, this is the e to the kx, and so you have 1 over k e to the kx when you anti-differentiate. But if you like, you can just go ahead and say, well, if we make it table ready, this would be negative 1/2 e to the negative 2x, and then we have negative 2 dx, if you want to basically do the format we always do. Or you can just say, well, if k is a constant, e to the kx dx, we can just say that's 1 over k e to the kx plus a constant, either way. But this is the method we've been doing all along. So if you want to stick with that, that's fine. So again, this is table ready. So du will just be 5 dx. And now v, again, this is ready to go. So this is just e to the u. So we get negative 1/2 e to the u, or e to the negative 2x. So again, don't worry about constants of integration with the what is it, indefinite integrals. We will tack on the constant at the end. So don't worry about trying to drag things along. That will not be required. And that's the beauty of the calculus, where we can be flexible with constants. I mean, not too flexible, but we can certainly be flexible. So now when you look at this, you're thinking, okay, well, we could do this integral, and then the one that's left will be likewise simple like this one was. So that was a good choice of u and dv. So now we have a plus, the diagonal, and then the minus with the integral. So this will give us, we have 5 times the negative 1/2, negative 5 halves x e to the negative 2x. Now, when we look at the integral here, notice we have a minus and a minus. When we multiply these together, they absorb. So we get plus, so we have a 5/2, and then we have e to the negative 2x dx. So again, I'm focusing on the fact that our choice was good because it left us with integrals that we can do that are very straightforward. Now, let's just go ahead and clean this up a little bit. If you like, and you know, there's a million ways to do these problems, but I'll go ahead and I'll wait to factor everything. So let's make this table ready just to keep it consistent with what we've been doing. So negative 1/2 e to the negative 2x negative 2 dx, just like we did here. So we get negative 5 halves x e to the negative 2x. And so here, of course, we'll get minus 5. We have 2 squared, so that's a 4. And this will just be e to the negative 2x. And then we can tack on our arbitrary constant. Now, when you look at this particular expression here, you're thinking, I'm okay with that. You know, type that in, you're done. Occasionally there is some focus about maybe making the problem look a little neater, but it's not required. So if you stopped your calculation here, you're fine. You're fine. Now, of course, in Calculus 1, most students always felt like, well, do I need to make it look neater? Do I need to factor it, you know, make it a little more user-friendly or whatever? And what we could do is just do a common denominator here. So if you like, we can say, okay, negative 5/4. And so that would just give us a 2x e to the negative 2x minus 5/4 e to the negative 2x plus a c. And then go ahead and factor. So now we can extract the negative 5/4 and the e to the negative 2x, if you like. Not required, certainly not required. And so that'll leave behind the 2x. And of course, we took all of that away, so plus 1. And this is just to showcase the fact that if you have the time, do it. But if you're working a problem and you know you finished it, click, 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 you're done. Okay. I think a lot of times as STEM professionals, especially as future engineers or computer scientists or mathematicians, physicists, whatever, we always tend to gravitate to a nice looking formula, even though it can be more trouble than we have time to put forth. So lots of times, you know, it's good to, you know, have confidence about what you're doing. And it does make the problem more complicated because you have to kind of streamline it to something very user-friendly and nice formula-wise. So again, what we see here is, and let me just make some comments here that are fairly obvious about this problem. You're thinking, you know, that 5x is really easy. You know, if we had to apply integration by parts the second time, Do we have to drag everything away from the problem like we did here in an integral and do it again? Well, you're thinking, if we get this new integral from this line, can we go ahead and say, there's my new u and there's my new dv, and apply the process again? Absolutely. So there'll be times when we won't write the integral down like we did here. We'll just say, okay, we've moved to the next level. This next integral, I'm still going to use parts. So I've got it set up with a new u and a new dv. I'm going to apply it one more time. So that is a streamlining process that we can often incorporate to save time of having to write down the integral again and just write down something that's redundant. Now, you have to think about the integration by parts mechanism to make sure that that makes sense to you. And then, of course, you can apply methods like that when they don't make sense. So the key here is to put in as many steps as you need, but always being able to look at how simple this problem could be. For instance, if you have something that is very simply differentiated, a polynomial that will eventually hit zero, you're thinking, oh, that's a quicker process, and you've got an antiderivative that's quick, that doesn't take a lot of work, then that is a way we can streamline the process if we need to. Now let's look at a definite integral. So I'm making these comments so when we come back to them, they won't be entirely strange. So let's look at a definite integral where we can use parts. So in this case, I've got the definite integral 0 to 1 of x inverse sine or arc sine of x squared dx. Now, we can actually integrate arc sine by itself like we did the logarithm, arc sine dx, with the same technique using parts. And the process is exactly the same. You differentiate it, and then the integral that results is something that's very doable. So parts is really good when you've got these integrands that just don't seem to work with anything we've done before. And now parts opens the door to the antiderivative, and a closed form at that. We don't even stop with an integral, which is sometimes the best we can do. So when you look at this and you think about what we have to do, I think what's interesting about this particular problem, if you think about it, is we certainly wouldn't want to tie this up in the dv, because that would be an integral that would require parts like I described to you, and that x squared would really be an issue. Okay, so now what we want to do is look at this in a very simple way like we did the previous problem, and work with things that we understand. So what we can do is say, okay, well, I'm just going to latch on to the inverse sine of x squared for the u, because we know how to differentiate arc sine or inverse sine. That's something we can do. And then we can latch on to x for the dv. Now, and then just stick this in there. So again, when we look at this, the first time you may not be able to see way down the road yet. But when you think about this, this would really be about the only way you could do this. I mean, the idea is that when nothing else seems to work, try parts. You know, and it's not going to be something that just jumps out at you. So don't be waiting for that aha moment until you've worked halfway through the problem, unfortunately. So now we'll do the derivative formula for the arc sine. So this will be 1. So we have du square root. I'll just use brackets for now. So we have 1 minus x squared squared to the 1/2. times the the derivative of x squared, which is 2x dx. Okay, well, that wasn't so bad. So let's write it again. We'll leave some space, just neaten it up a little bit. So we have what, 2x dx, and we have 1 minus x to the fourth to the 1/2. So we're confident that we understand that. That was the first lecture. And now, of course, here we're like, well, add 1 divided by the new power, right? So v will be x squared over 2. But this is good because now that's going to give us a power of 3, which is going to work really well with the x to the fourth here in the denominator. So this may not have been too obvious when you started, but at least now you're thinking this was not a bad way to go. It was actually the only way. So now you can say, all right, well, we can connect. Now you don't have to draw these arrows, but I do think it helps to give a little assistance to the process that we're trying to accomplish. So now, of course, we've got our 0 to 1. So we're going to take the product here. So we have 1/2 x squared inverse sine of x squared evaluated 0 to 1. So with the UV part, we just go ahead and slap on the limits of integration. That's ready to go. But with the integral, we will put the limits, in their positions on the integral sign. So now if we look at this, we have the minus, no additional minuses. Notice here the twos will absorb. See here, the 2 and the 1/2, they will absorb. So this will be minus the integral 0 to 1. 2 times 1/2 is 1. That gives us an x cubed. And then downstairs we have 1 minus x to the fourth 1/2 dx. So what's interesting about this particular problem is that we really only had one way to do it. And so we just said, okay, we'll try it out. Maybe we need another technique that's going to come later in the class. But now this is good. So we can go ahead and look at this. And then, of course, we can make this table ready and be done with it. So this will be 1/2. We'll substitute 1. So that'll just be a 1 squared. And then inverse sine, well, 1 squared, that's just 1. I just put a 1 there if you like. And then, of course, the 0, well, that's just going to zero out everything. The 0 here and the, well, so we'll just say, I'll just do a minus 0. You can write more there, ladies and gentlemen, but when it's clear that this will just be a 0, just remind yourself that the value there at the lower limit is 0 without having to write additional. I think that's sufficient. And of course, it just reminds you of what you actually did mentally. You can write all of this out, but yeah, it's just like when we do the antiderivatives with the other applications in chapter 7, we'll just put the 0 in parentheses, saying that this annihilates the actual antiderivative there. And now, of course, we want to make this table ready. So now you can think of the u as 1 minus x to the fourth. So, well, of course, I can't use u anymore. We've already used it. Sorry. I guess I'll use w or omega. So that's a negative 4x cubed dx. So this requires that we have a negative 4 in the differential, and then we can pay for it. So we have minus negative 1/4, 0 to 1. Now we have what? We've got what? X cubed, then negative 4 dx. Just kind of putting it to the side. You could just write it up front if you want. Well, let's make it even easier. We're working too hard. Let's move that radical upstairs. Make it easy on us. So 1 minus x to the fourth to the negative 1/2. And now I'll just do this. I'll just do the negative 4x cubed dx. So that's table ready. So again, just to help ourselves out, we'll go ahead and move the radical upstairs so we can easily apply the power rule, which we've done a million times. So now we have 1/2. And then of course we know this, the inverse sine of 1 is pi over 2. So we get pi over 2. Now we have plus 1/4. Now this is table ready. Let me write that, table ready. So we add 1 divided by the new power. So plus, so the new power is 1/2. So that'll be times the 2 over 1. 1 minus x to the 4th to the 1/2, 0 to 1. You know, we keep doing the same thing over and over, but good. It makes you better at what you're doing, because these standard techniques, that's why Calculus 1 and Pre-Cal are so important. That's all we do. We learn a little bit of new stuff, and then we're doing the same thing over and over. So now we have pi over 4. And now here we've got a, what? We've got a 1/2, 2 over 4. So if we substitute the 1, notice the 1 minus 1 to the 4th, that annihilates. So we can just put a 0 there. We can do that mentally. And then the 0 here, of course, we've got the minus. So this will be minus 1 to the 1/2. So now when we look at this, and another thing that's interesting here is we can make this look nicer. I always think about how we can do that, but this is pi over 4. So we have a 1/2 minus a 1, or times a negative 1. So minus 1/2. So we can dress this up a little bit. Just get a common denominator and then factor the 1/4. Yeah, that's not required, but again, looks nice in a presentation. So of course, if you wanted to stop here, that's fine. But if you want to dress it up like we've been doing, we can. I mean, I think once you get to this point in the problem, you're like, okay, that looks fine, and we get a check, and WebAssign gives us a thumbs up, so we're fine with that. I just know that as an undergraduate, every book I ever picked up, all the answers look so beautiful, and I'm thinking, why did they do this? And then after you get used to it, you just kind of want to do it, you know, but it's not required. This is certainly fine. And okay, so what I wanted to show you here is that when you do a definite integral, everything's the same. You apply the limits to the UV, and then you apply the limits to the integral. So you do it the same way, but remember, part of the antiderivative is already taken care of here. So you just apply the limits as you normally would in a problem. So that's the standard way. But then of course, with the integration by parts, you have this integral. So you just attach the limits as you would if you were just starting over. So the thing here is that the definite integral is a little bit more work because there's more stuff, but not an excessive amount of work. Okay, let's try another definite. I think these are good practice. And when you do the definite and you mix it in with the new technique, it's good experience. Let's see here. Yeah, here's a good one. Let's see here. 0 to pi over 8. And we want to, you know, get this down. That I'm throwing in a little bit of trig to get us ready for the next section. But these techniques, the more you practice, the better you get. You can't practice forever. But with the integration techniques, just practice. That's all you can do. It's like factoring. you know, when you were in Algebra 1 and you learned how to factor. And then, of course, you didn't probably do very well. So when you got to college algebra or pre-cal, you really honed your techniques. But how do you improve at factoring? You just practice. So that's all you really have to do here. Don't feel like you have to do a million problems, but do enough to where your confidence is good. So now when we look at this and we think, okay, you know, we've got those derivatives. We know the derivative of tangent is the secant squared. So that makes for an easy antiderivative here. So we're thinking, you know, when we look at something like this, this would be a great example for integration by parts. But in general, the secant integral is not easy. So we lucked out here. So in this case, what we'll do is say, okay, u will just attach to the x, keeping in mind that we don't want the integral to be worse. So if we threw the x over here with the dv, that's going to make an integral that's even worse than the beginning one. So if you think a little bit outside of the box and think, well, if I actually do this, what am I going to get when I just multiply? Think mentally in your head about, you know, wait a minute, what's going to happen here? And like, no, that's not going to work. So just remember the key is to produce an integral that either you can algebraically manipulate or the actual integral is just easy. It's doable. Okay. So that's the important thing. So now we'll have dv will be the secant squared 2x dx. Again, remembering the derivative formula from pre-cal, or not pre-cal, cal 1. Yeah, I don't think pre-cal would have been too good with this. So first, of course, you know, we'll make this table ready. We have the u, or the, I guess, omega here. So we need a 1/2. All we use, again, I know I sound like a broken record, but the techniques are all based on calculus 1. I remember I tutored a student in graduate school. The young lady said, well, my teacher in high school said, if you can't do integration by substitution, you'll never make it. I said, well, I don't know about that. I said, you might have to practice a little bit more. But she said, there's a time when we all decide if we're going to be an engineer or not. And I said, well, maybe, but I think she finally saw the light. And she's like, I'm going to make it. And so that's good. I mean, even if it's delayed a little bit, it doesn't matter. That it eventually happens is good. So now we're ready to go with this. And of course, we wait for integrals like this, right, or derivatives. We just get what, dx, right? So now let's go ahead and write down the v. Remember, this is table ready, so we're going to have 1/2 tangent 2x. Now, when you think about this process, when you think about the process, you're going over in your mind, what were the derivatives we learned in Cal 1? What are those easy integrals? You know, but we know that we have to work a little bit harder with tangent because that's a du over u. But at least this one was straightforward. Okay, so now uv minus the integral v du. So now, just like before, we have our 1/2 x, 1/2 x, and then tangent 2x, evaluated 0, pi over 8, okay? Just like that. Just like we had in the previous problem. And now here, of course, notice we have a minus, got a 1/2. I'll leave a little space. And we have tangent 2x. And of course, we have our limit 0, pi over 8. Now, of course, like we did before, we have to make this table ready and get this ready to go. Now, notice, again, we have an omega here, which is a 2x. So we're going to need a 2 in the dx, in the differential, actually. And so we'll have to pay for it right here with a 1/2. So again, let me just, since we kind of wrote this down, just put boxes around this to make this table ready. I want us to get good at table ready because when we use integral tables in a formal way, we have to do this first. And we need to be good at it because the integral tables won't be difficult, but there are times when if you're not thinking about what you're doing, you can really just make some careless mistakes. And careless is easy in calculus. So we need to make sure that we're getting this well. So now we're good to go. So let's go ahead and apply the fundamental theorem. So we have the 1/2. So we've got pi over 8. And then we have tangent. Now notice we have the 2 times the pi over 8. So the 2 will absorb into the 8 and give us pi over 4. So we can do that calculation there, all right? So again, 2 times the pi over 8 will give us pi over 4. So that's good. Now, of course, the lower limit, again, we can see here, that's going to 0 the x, and we're done with that. So we'll just say minus 0, since that's annihilated. Now we have the minus 1/4. But notice here, this is table ready, but this is the negative natural log of the absolute value of cosine 2x. So again, we have a negative natural log of the absolute value of cosine of 2x, evaluated what? 0 pi over 8. So what we see here is the tangent integral, just a blast from the past, tangent u du is the negative natural log of the absolute value of cosine u plus a constant. So that's an important formula, one of our standard formulas in the 1 through 20 that I gave you in the PDF. So now, again, tangent of pi over 4 is 1. That's it, cosine and sine are both 1 over root 2. So we get 1/2 times pi over 8 times a 1. Now we have minus minus, so this is plus a 1/4. And now we can substitute the pi over 8. So we have natural log of the cosine, same thing before. Remember, the 2 absorbs into the 8 to give us pi over 4. So pi over 4. And then we have natural log of the cosine. Of course, now 0, that'll give us 2 times 0, which is 0. So cosine of 0, right there. Now, when we look at this just gives us what? Pi divided by 16, 2 times 8, plus 1/4. Now, what does this give us? Well, we have the natural log. Again, the cosine of pi over 4 is 1 over root 2. So we could say this is natural log. And we can, here, 1 over root 2, how can we write that? We can just say 2 to the negative 1/2. So let me just write this up here. Here's a very slick way to write this. Cosine of pi over 4 is 1 over root 2, which is 2 to the negative 1/2. I know that's not earth-shattering, but that certainly allows us to use the power rule for the natural logarithm. Okay, and then we have, what's cosine of 0? That's 1, so we have ln of 1. Oh, and let me put in my 1/6. So we have pi over 16. And so this is plus 1/4. And so now by the power rule, this will be a negative 1/2 ln of 2. And then, of course, log of 1 is 0. So this gives us pi over 16. So we get minus 1/8. I don't want to write that 1 for some reason, ln2. Now, of course, you can factor this, get a common denominator if you want, beat it to death. But this is fine here. Okay, so the actual calculations here are just what we've been doing. No, nothing new, nothing new. Most of what we do is, like I say, repetitive. But what we're seeing here is that this integration by parts is introducing a very powerful technique. It is opening the door to product antiderivatives. Again, you look at that in Cal 1 and like, I've got some work to do. So it's kind of mysterious when you think about it, but rather profound that you just take, it's like this, are there other derivative formulas that give us a great technique like this? Well, not really, but this one will suffice. So good for us. Now, let's see here. Oh, we need to do another repetitive thing. We need to do another algebraic. I've got several ideas here, but let's do one that's algebraic. Okay, like we did at the very beginning. In the sense that when you look at it, you're going to think, well, these are easy. The idea that we notice with the cosine squared is that if we apply parts after one pass, one application, just one application, the integral repeated, if we use the fundamental trig identity. That's pretty good. We're going to see that again. In this next example, we're going to see that we need 2 applications, and I'm going to show you a technique that will make it much more manageable. Okay, this is what I was talking about before. So say we have the following, and this, you can use integration by parts to generate some really nice integral table formulas. I mean, I often do one with this type of problem. And when you get to differential equations and Laplace transform, you're going to need a way to work the integration by parts problems quickly. And so you won't have to start from scratch. You can just use your integral table, knock out the parts integrals, get that Laplace transform, and move the differential equation problem forward to make it more efficient. Now, when you look at this example, again, you can throw some limits on here, and there's a WebAssign problem where that's the case. But I want to focus just on the algebra here. I want to make a comment that's very important. Notice that when you start differentiating or anti-differentiating the exponential here, the result is another exponential of the same kind. That is when you think about the method of undetermined coefficients in differential equations, it is based on the fact that when you differentiate, you get a function that's like the one you started with, in the sense that it doesn't change appreciably. And if it does, then the method, not so good. So again, same thing with the sine. We know if we integrate or differentiate sine, after 2 applications of those processes, we're back to the same type of function, accepting some constant, okay? And so we're thinking algebraic. So what I want to do is maybe suggest integration by parts with 2 applications. But instead of writing down the first integral after the first application, is let that choose the new u and dv and apply it one more time. And then only look at the final integral to introduce the algebra. That's what I was talking about before. Okay, so here's what we're going to do. The first thing I'm going to do is I'm just going to differentiate the sign because those are easy. You don't have to work so hard to keep track of signs with those. E to the minus 3x, we can just do the minus 1/3, in our head type thing. So I'm going to set this up so we actually differentiate the trig function and we integrate the exponential function because that's easier. Now, what I'm going to introduce now, we're not going to keep track of the differential notation. We're going to differentiate one column and we're going to anti-differentiate another column and apply this twice. So what we're going to say is apply parts, that'll be shorthand, twice. Apply it twice, and this will be algebraic. This is algebraic. So now, and let me check yeah, that looks better. So here's what I propose. Let's do a D column. This is where we're getting a little bit more relaxed, more like the Oliver Heaviside approach, the famous mathematician and engineer from Great Britain. His techniques are widely used to this day. And this was over 100 years when he lived, maybe even more than that. My history's not so great with math, but I certainly appreciate it. And the integration. So our U will be the sine. I'm not even going to write U equals sine 5x. And the dV will be e to the negative 3x. And I'm not going to worry about typing the dx. I'll just remember when I do the integral finally that I'll drag along a dx. So I'm not going to worry about that right now. You can put it in if you want, but now this is less formal, but more streamlined. So there's the U, there's the dV. Okay, let's apply the process. So we get 5 cosine 5x. And of course, that'd be a dx, but we're just going to keep it simple here for now. So take the derivative here, sine of 5x, we'll have the cosine of 5x times the chain rule, which will give us 5. And now here we can go ahead and just think table ready and use my little formula where we just do 1 over k. So this will be minus 1/3 e to the negative 3x. Okay? So if we were applying this once, we would say uv, and then we'd go across here and get the integral. And then you'd apply parts to the integral that we just wrote down. We don't need to do that. There's the new u and there's the new dv right there. So I'll say, don't write down the integral again. We'll just say apply. I'm just going to write here, apply parts. The second time right there. So instead of writing the new integral and keeping track of this, which we can easily do with the diagonal line, let's just apply it again. This is the new u, the new dv. Do it one more time. So now, okay, well, that's easy enough. We'll get a negative sine 5x, but of course, in another 5, that's going to give us a negative 25 sine 5x. So again, differentiate, we get negative 5 sine 5x times 5 gives us a negative 25. And now, of course, here, notice we'll get another copy of negative 1/3. Negative 1/3 times negative 1/3. I'll write this one out. That's easy, but this is a little bit more complicated. E to the negative 3x. So this will just give us 1/9 e to the negative 3x. Now this is where you can see that when we go across here with the integral, we get an integrand with a sine and an e to the negative 3x in it, which is going to make this algebraic. So that's what I was talking about. 2 applications, and we're back to a copy of the integrand accepting constants. So now we say this is where we alternate the signs. That's why I put the plus here. And now with the integration with the negative, we have the minus. Now the first horizontal line was a negative, but when we apply it again, that negative becomes positive. So the horizontal lines also alternate in sign, and this will be a plus. So this is where you have to think about the fact that we're applying UV minus VDU, and that minus sign pushes the alternation in sign with the diagonal lines. So the diagonals plus, plus, horizontals minus, plus, etc. So this is where I talk about the fact that we lessen the formality of the notation to see the algebra that ensues. And so now the original integral is now algebraic. Now here's what I'm going to do. That writing that down a million times is a waste of time. Let's just call it A. Why not? I mean, you know, you can keep writing it down and then your hand starts to ache. So now we say, okay, the original integral was A. And so now we're going to connect everything. So we got a negative 1/3 e to the negative 3x sine 5x. So that takes care of this one right here. Now notice we have the negative, the 5, the negative, and the 1/9 term. So we have, in this case, minus 1/9 e to the negative 3x right here, 1/9 e to the negative 3x minus, and then we've got the 5. So let me stick the 5 up here. Just kind of put it right there, 5, and then cosine 5x. So what we're seeing in this particular process here is that this is the same. Again, the 5, the 1/9, 5/9, negative, negative, cosine, cosine, e term right there. And then the very last one, notice we've got the plus here, but we have the what? 1/9 and the negative 25. So this will be minus 25 over 9. And this carries the integral sign of this, which is the original. So what I want to do here and what I want to make very obvious here is that when you take the horizontal line, you carry the integral, and it's the same integral we have, except for that number there. And now it's algebraic. It's like solving for x. So you make this process algebraic, but if you put too much notation into the process, then you lose your way. And I refined this technique as an undergraduate. This is something I refined myself as an undergraduate. When I got to grad school, I had colleagues that said, well, that's not going to work. That's not going to work. I said, excuse me, let me show you. And then they're like, well, dang, you should write this up. I said, no, I don't need to write this up. This should be obvious. So I've even had students go to the university and they send me emails. Now, how did you do that integration by parts that you taught us? I forgot. I said, well, you shouldn't have forgotten. So I remind them about it. And then they tell their professors about it. But it's basically taking the Larson technique, but avoiding writing down unnecessary integrals and just applying the process again. And then keeping the alternation in sign with the horizontal, the diagonal and horizontal arrows. So now take this over. And of course, we could go ahead and do a common denominator there. So this will be A. So we have 1 plus 25 over 9 equals, so we'll get a common denominator, negative 3 over 9 e to the negative 3x sine 5x minus 5 over 9 e to the negative 3x cosine 5x. Now, if you can see here, this is just going to be a 9 over 9. So this is going to be 9 plus 25, which is 34. So we have 34 over 9 times A. equals all of this. And so if you like here, we can, and notice what's nice about this is that these nines are gonna absorb. So I'll just say here, let's do this. Negative 1/9 e to the negative 3x, since those are common, and that's going to leave a 3 times sine 5x. And then, of course, if we factor the negative in the e, that's going to leave a plus 5 cosine 5x. So what's nice about what I'm doing here is that it makes it much more user-friendly, and the algebra is cleaner. So now notice here, the nines absorb, and then the 34 just comes in here. So a, which is the original integral, this is a little bit cleaner. If I do it this way, it's less writing. Always teach things differently, because as I teach, I think of ways to streamline things. Of course, there are times when I come up with new things that I have to throw in the trash can because they don't work. I mean, not everything's going to work nicely. So notice these absorb, absorb. So we divide by the negative, or excuse me, by the 34, and that gives us a negative 1 over 34. So this gives us, so negative e to the negative 3x over 34. And then we'll tack on our constant 3 sine 5x. That way you just don't have to keep writing plus c. If you want, fine, that's okay. I think we're fine here. When we finish, we write the most general antiderivative. So if you don't want to, put the plus c through here, that's certainly okay. That it doesn't make it wrong. It's just that I won't, like, oh, okay, well, you need to do the plus c here, and it's all right. It's all right. So now, when you look at this example here, you can see, and what I'm doing is I'm comparing this to a derivation I did. What you can see here with this process is that the power coefficient here of the exponential, and also in the argument of the sine, these constants start to show up. And here, this is just what? This is just negative 3 squared plus 5 squared, which is 34. So you can see how this generates a nice integral formula. If you want to use an alpha and a beta, or an a and a b, you can use this same process and generate a beautiful integration table formula. And so what I tried to do was write this exactly how you would see it in an integral table, where you would have the square of the constants here, and then you have the factored exponential term, and then the trig terms inside. So what's important about this particular technique, and this is a very useful technique, I mean, what I found is if there's no attempt to streamline the process, students never seem to get any of this correct. The thing is that if you look at the process as being applied twice, and simply associating these two terms as the new u and the new dv, and applying the process one more time, then you see the repetition of the integrand, which makes this algebraic. Now, if you don't want to call this a, you can simply write this down and do the same thing. But I want to focus on the fact, unlike I did before, that now this is algebraic. And if you solve for a, you're basically solving for the original integral. So that might be a way to make the algebra a little more apparent to you. And then, of course, this helps to organize the process. Like I say, it's amazing that it's not written up this way in books, because it's so simple to keep track of things. Now, Heaviside, he tried to do everything when it was possible in a tabular method, when things would zero out. But notice nothing here zeroes out. I basically just took his method and adjusted it for this kind of problem. because I thought his method was really ingenious the first time I saw it. And I had to think about it. I said, why is this working? I said, oh, I said, they're just applying the process without writing the integral down. The new U, the new dv, and do it again. And it makes perfect sense. So if one side zeroes out, then all you have is a bunch of diagonal lines and no horizontals. But that only happens when you have a simple polynomial as one of the products that you differentiate to zero. So that'll be a nice technique. Okay, so again, this will be something that you will use over and over in engineering and physics. It's a standard integral, and you will see this written up in the integral tables all over the place. Now, I wanted to do an example having to do with a trig integral that comes up. We normally see it, you know, when we think about doing trig integrals. And you're thinking, oh, you're just going to use a trig identity and just knock it out like you did with the cosine squared or the sine squared. And I'm like, almost. But when we think of integrals of secant, if we don't have tangents hanging around, powers of secant can be really difficult. And you're thinking, well, oh, I bet with that kind of problem, we could use parts to do a reduction formula for positive integer powers of secant, just like we would do for sine, cosine, tangent, whatever. But here's a type of integral that actually repeats or comes up quite a lot in the literature. And so we want to know how to do it. And it's just the plain old secant. And I won't, you know, change up the argument. I could make it harder, but I'll just go ahead and leave the argument in as x. And then, of course, as next class, we'll throw in 2x and 3x and keep you busy making everything table ready. Because if it's not table ready, then then the coefficients get confused. So we'll just start with this. Now, what I wanted to focus on here was the same technique we used before in a previous problem. So I thought this might make a good follow-up. So when you look at this, you're thinking integration by parts. And because we used a particular technique before, we're thinking this will work again. So what we want to do is to say, okay, we know if we have a secant squared term, then we can set that up as the dv like we did before and get the tangent. Okay, so the idea is that this process will also work for this problem, but this turns out to be algebraic with only one pass, just like we did with the cosine squared. So again, we want to use integration by parts. So I'm just going to say use parts, and this is algebraic. I'm trying to focus on some examples that occur often in the literature, so that if you have these examples down, then you can apply these techniques to other problems without feeling like you have to do, 200 examples. If you can learn some really good techniques, you'll find that you can repeat those techniques to do other problems. So now what we're going to do is say, okay, let's do secant x and secant squared. So by doing that, we set this problem up like we did for the last one. So now, again, we'll say u. Now I'm going to do this formally, but you don't have to. You can do your D column and your I column. I'm just going to go ahead and do this formally because it only takes one pass. And if I had two passes, I wouldn't put in all the DXs and stuff because then that gets messy. So with just one pass, you can write it like we normally do. Your choice though. So we have secant x dv. I like the D and the I, but I don't want you to think that's the only way to do it. If you look at my lecture notes, you see I use that all the time. And it's kind of become my trademark, but you feel free to use whatever notation helps you with your understanding. So now, of course, we're at a point where we certainly know the derivative of secant, and then the antiderivative here is the tangent as we had before. So now du will be secant tangent dx. And then, of course, here, this is table ready. V is just tangent x. We like the simple ones. So now you can see this is definitely going to be algebraic. So we have plus and a minus. So this just takes one application. One application. Or sometimes I'll say one pass. So now, well, let's see what we have. Okay, so I'll be real formal this time. I'll just say I'll go ahead and write it out to give you another way to look at it. So we have secant tangent. Isn't it nice to do a problem that doesn't have, coefficients and negatives and positives running around? I mean, it does make it easier. And then now notice here we have a minus, but now we get a tangent squared times the secant. So we have minus, in this case, I'll just write secant x tangent squared x dx. Now, this is exactly like I did with the cosine squared at the beginning, and that's why I did it, because you've already seen me use a Pythagorean identity to rewrite the integrand. And so in this case, what are we going to do? Pythagorean. So notice that we have 1 plus tangent squared x equals secant squared x. So that's the Pythagorean identity that relates the tangent squared to the secant squared. So we replace tangent squared with secant squared minus 1. So equivalently, we have the integral of secant cubed equals secant x tangent x minus the integral secant x, Pythagorean identity, secant squared minus 1 dx. And now, of course, we have the original integral. Now, of course, that's why you see why I like to write a, but this is okay. Just showing you how it looks if we don't make any substitutions for the original integral. So we have secant x, tangent x. And now, of course, you see we have the secant times the secant squared, which is secant cubed. So we get minus secant cubed, which is repetition of the original integrand. And here we have a minus minus. So here we have plus the integral of secant. Secant times the -1 times the minus gives us plus the integral of secant using the linearity of the antiderivative. So now you definitely see this as algebraic. We have a copy of the original integral here. So this is the minus a, and that's the a. So we add this to both sides. This is now algebraic. So equivalently, we have 2 times the original integral. And now, of course, we have secant x, tangent x. And now, of course, this is our famous formula from Calculus 1, the Lagrange formula. This is the natural log of the absolute value of secant plus tangent. So that's this problem uses all the bells and whistles that you learned in Calculus 1 and always forget, okay? So again, we're using all of the standard calculus with the secants and the tangents. The antiderivative, the secant squared is the tangent, the fundamental Pythagorean identity, and then the Lagrange formula for the integral of the secant, which is the du over u, once you manipulate it. Now, of course, if we divide everything by 2 and tack on the constant, we're done. So equivalently, the integral of secant cubed, which, trust me, does come up often, we'll just be dividing all of these by 2. So it's conventional or convention to just write as a 1/2. And we have secant x
tangent x plus natural log secant x plus tangent x. And then we can tack on the arbitrary constant. So when you, again, all of these formulas where we have these integer powers of these trig functions can be written in terms of reduction formulas. Some of them are very powerful. However, you think about that, it's like if you have a formula, you can kind of, look at it in terms of what am I saying? Look at it in terms of maybe an algebraic manifestation, or you can start with the formula and prove it inductively. You're thinking the induction method is probably a good way to motivate the actual formula, or at least to prove it. That's where mathematicians kind of toggle between, okay, we have an algebraic manifestation here, and so that's good enough. But it's kind of like the purists like to say, well, let's just go ahead and tap that nail perfectly, make it just right, and do an induction proof. So, induction basically takes a formula about natural numbers where you verify it for 1 or 2, and then you assume that it's true for some arbitrary natural number and show that that makes it true for the following one or the successive one. So that kind of covers the infinite case. So there are many ways to go about these formulas that again are good, and so don't feel overwhelmed with this method. Just look at it as a door opener that now we don't have to just stand back and think, well, I wish I could integrate this. Now we see integration by parts offers a very, very important technique. Now, I did want to make a comment. There's a nice example in your WebAssign about some Fourier coefficients that use integration by parts. But what I wanted to show you, I just want to get this started, and I'll try to finish it up maybe at the next class if I don't have time, is to give you an example of miscellaneous substitution. That is, when we did a lot of the problems with the area of a surface of revolution, with that distance to the axis of revolution, we were sometimes stuck with a radical and a power of x, and we did miscellaneous, okay? Well, the integration by parts takes care of that. Now, most students will say, well, I don't, I'm okay with miscellaneous, and that's fine. It doesn't matter. And it makes no difference. But what I do want to show you is that with the miscellaneous technique, you can actually streamline the process, and maybe it's a little bit easier. Now, of course, if you want to make the problem look beautiful, and make it look all pristine for a textbook, then you got a lot of algebra to do. But let me just give you an example here in closing. And if I want to say more about this, I may mention more of this on the next class, or just have you complete it. Here we have x squared, which is a nice polynomial. And we have, I'm going to write this without the radical. We have x minus 4 to the 1/2 dx. So if you wanted an integral of this, a closed form antiderivative, you want to get in and get out, and maybe you're not worried that it looked too beautiful, but you just want to get an answer. Well, let me propose a way to do it. Now, what you want to notice here is that in this particular example, we have a very simple product here. That is, x squared differentiates to 0. And then, of course, x minus 4 to the 1/2 is an easy antiderivative. It's add 1, divide by the new power. And the differential here, if we did d omega, is just dx. So there's no constants to even worry about. We just have to divide by the new power. So we're thinking, That's not a bad way to look at this. So I would say use parts. And I'll just say miscellaneous will work, or miscellaneous does apply. And I'll say miscellaneous sub right there. So how would we do this based on the techniques? Now, this is famous. This is where Oliver Heaviside became very famous. And this is what he termed his shortcut method. So just like we have before, we can think of applying this process successively without writing the integral each time, picking the new u and the dv as we did with the e to the x trig function, sine type function. So we can look at something like this. So we have an x squared, and then we have x, and again, don't write the dx, you don't need to. We can do this informally and get plenty of good work here. So when we look at this, we're thinking, okay, well, we can differentiate this down to 0. So we're thinking, let's apply it once, 2x. Okay, so here, add 1, divide by the new power. Well, the differential doesn't alter. D omega is dx. So if we add 1, we get 3/2. So we get 2/3 x minus 4 to the 3/2. I mean, that's so simple. You're thinking, it can't be this easy. Well, it is. And this is easier than miscellaneous. Now, you're thinking, okay, I do the UV and then I do the other integral. Well, don't do that. Don't do that. Because look at this as a second application. So I'll say apply again. Apply again. Think of this as here's the new integral, here's the new u and the new dv. So why write down the integral? Just apply it again. Okay, what's the derivative of 2x? That's 2. Now we're thinking, okay, we've got this coefficient out here. Add 1, divide by the new power. What's the new power? 5/2. Flip it, 2/5. So we get 2/3 times 2/5 x minus 4 to the 5/2. Right there. Amazing. Okay, and then of course we multiply this out, but we'll do it in a way that makes sense. You never multiply anything in calculus. You're going forwards to go backwards. You multiply when you're done. You keep things factored so you can factor. You know, I mean, it's like, I don't know why that's not obvious. Now you're thinking, integrate. I do it again. No. Let's do it one more time. What's the derivative of 2? 0. 0. So that integral is going to be obliterated. There won't be anything left. So now add 1, divide by the new power. What's the new power? 7/2. So we have 2/3 times 2/5 times 2/7. X minus 4 to the 7/2. This method is so efficient that, you know, when I teach miscellaneous, I always tell my Cal 1 students, I say, I'm going to show you another way to do this, and I think you're going to like it. But of course, at the time, they're just struggling with miscellaneous. So now look at this. If we come across here, we're done. There's nothing left. So this process utilizes the fact that the polynomial here differentiates to 0. And so the last integral is just 0. You're thinking, well, you just beat it to death till there was nothing left. And so now you have your diagonal lines plus from the parts formula minus and plus. And so now, and I'll have you do some algebra on this to make it look beautiful. So this implies equivalently that x squared x minus 4 to the 1/2 dx is now, and just go ahead and multiply it out, 2/3 x squared x minus 4 to the 3/2 minus, going to put down all these, 2/3 times 2/5 times 2x, keeping track of everything, x minus 4 to the 5/2, and then the last one, plus 2/3 times 2/5 times 2/7 times the 2, x minus 4 to the 7/2 plus a constant. Now, when you look at this and you think about this, you're thinking, there it is, not very beautiful. But here's the thing, that's an antiderivative right there. Now, what I've done in my notes and what I normally do is that you're thinking you can make this look really nice because of the power rule. Once you factor the fractional part, then what's left is a polynomial. So when you look at this, 2/3 x squared times the radical minus 2x 2/3 2/5 times the radical plus 2/3 2/5 2/7 times the radical. At this point, here's what I want you to do. Just try this out. Clean it up, factor the least power of the radical, which is the 3/2 power, common denominator, and leave everything multiplied until you need to start putting things together like I've taught you and get a nice, beautiful answer. So if all you're interested in is knocking out an antiderivative, there it is right there. And miscellaneous would have taken you much longer. So the beauty of integration by parts is that with certain types of integrands, the process is very simple. So again, I want you to think about this and think about how it works and how you simply reapply the process without writing down the integral again. If you write the integral again and you choose the same terms for u and dv, then to write it down and write it over, it becomes very redundant. So this is a process which Heaviside termed his shortcut method. Shortcut method. Now, the beauty of it is that it's efficient and you keep track of your signs. And so that's a nice method that I think you'll be able to use many times over. But you do not apply this method unless it's applicable. That's the thing. Students say, well, I'm just going to apply this to everything. Well, no, if you do that, then you'll get all the problems wrong. So the beauty is being able to discern when you can minimize the work. But the minimizing or making the work more efficient depends that you understand the process. And so if again, when I do this, I'm using the fact that I've taught you the integration by parts and how you don't have to write the integral down each time. That cuts out one level of the process that makes the routine more efficient. Okay, so enjoy working on this. This is very important. Spend time on this. The review integrals are not difficult. And then I've done nice lectures to finish up that and the center of mass. So you've got all the content that you need. And I'm thankful that we've got some nice weather. So thank you for your attendance today. I hope you enjoyed the integration by parts. And I'm sorry I went over a couple of minutes, but I have 2 office hours today. And please come by to see me if you have questions. And of course, I have office hours on Tuesday. So take care. And if I don't see you at the conference hours, I'll see you at our next lecture. Everybody take care and see you later.